Alright.
Yeah, so, well, that's always the bottom line.
Yeah,
You
yeah.
know, the bottom line is.
Does that work? Yes, it does.
How do I get out of this?
All right, why don't we get started here? Well, good afternoon, everyone. Welcome to our first Tuesday of the new sort of academic year, and the first one we've had live in quite a while. So we're hoping that we can do this ongoing, and there's a list that's out there, right, of the.
Yeah, we have the dates right up there.
So just to bring to your attention, there's several upcoming events that I'd like to make you aware of. We'll come back to this one. This is our speaker today, obviously, and Asif Sheikh will introduce him in just a second. We have neuroprosthesis seminars in September, October, and December, and we're working on November. No?
November.
Oh, I forgot. November, there's a very special speaker. That's me, and we're going to do the State of the FES Center again. We'll do this live, first time in a few years. So we're hoping to get back a little bit on track here with some live activities, and that's it for me. Welcome, and I'm going to turn it over to Asif Sheikh to introduce our speaker today.
Thank you, everyone. Thank you, Dr. Kirsch. Thanks, Cheryl, FES staff, for organizing this. There are more people coming. It is, we are fortunate that Dr. Charlie Duffy, who joined our faculty and our family, our group, a few months back. Dr. Duffy is very soon Reynolds Professor of Neurology. And currently he is the head of Behavioral Health and Memory Center, BHM, at University Hospitals, which is basically his head of cognitive neurology. He was for a long time at University of Rochester, where he did a lot of experiments and studies on non-human primate single unit physiology, looking at path and path detection and perception, right? And then recently he has been working more on the human end of the system. From University of Rochester for a short period of time, he was at Penn State, and from there he moved to our department. Without any further delay, Dr. Duffy.
Thank you all for taking some time out in what I know is busy days to let me harangue you, just talk to you about the kind of stuff I do. I understood from the schedule that this was a 20-minute talk. Is that right? Yes. Yes. So I'm going to try to cover some ground more quickly than I perhaps usually would, and give you some idea of what I do and why I do it.
There's a PowerPoint.
Oh,
Or if you want to just hit share screen.
okay.
There you go.
There I am. Terrific.
And you have to share at the bottom.
Something like that. Is that okay? Is that okay? Good, good, good. Well, so I work on Alzheimer's disease. I've been working.
It's actually the wrong screen is shared. Cheryl, can you swap which screen is up like you did before?
Sure.
I'm sorry.
Oh, I apologize.
It should be under display settings right at the top middle.
Middle.
No.
What if we just escape?
And then Come on.
You want to stop share first? Oh, it's not sharing? No, it is sharing. Isn't it?
That looks great.
Okay. And then you have to go back, right?
Oh, wait,
Yeah, so.
I think it's right down there.
Oh, okay, yeah, this is where to start. Sorry for the technical difficulties. I see. So I work, as I was saying, I work on Alzheimer's disease. I started out with that interest when my
I have to sneak in there again. I apologize. We still don't have it correct.
when my then beloved professor during my residency, C. Miller Fisher, I found spending time on the wards, talking to and examining a patient who was just stuck in our unit. Oh, thank you.
I need this.
Because we couldn't place him. And he went back to him and back to him. And he would, once on rounds, and I was, when I was the senior resident with the crew,
All right, we're good.
he stopped me and asked me, well, what's going on with this patient? And I said, well, he just has Alzheimer's disease. And I wasn't at all interested in Alzheimer's. I didn't know Fisher was at all interested in Alzheimer's. And so, and Fisher had a great way when you said something stupid of going, oh, then you knew you'd said something really stupid. And he asked me about, well, why does he do that? I went, gee, I don't know. He is doing a kind of trichophytomania kind of thing. And that sunk in my head. And when I started my postdoc at NIH, one day I discovered that Fisher had just published back-to-back papers on clinical phenomenology and Alzheimer's disease, something he'd never worked on before. And of course, I read those papers avidly, and it planted a thought in my mind. And then later on, I had this experience where a patient who was admitted in Rochester told me that he was getting lost. We sat down together, and I understood what was going on a little bit. And I as I got on the elevator to go home that night, I remember just talking to him and pushing the button and saying to myself, it sounds to me like he can't do the thing that I'm studying in monkeys. And I thought, well, that's ridiculous. And then I thought, if that's true, and I don't figure it out, it'll be really embarrassing. And so I shifted my gears a little bit. Now, another thing happened at that time too. That was Christmas a long time ago, and my mother came to visit, and I recognized that she had Alzheimer's disease. So I went into my department chair, I'd been there for about 6 months, and said, you know, all that stuff I said I was going to do about epilepsy, because I was an epileptologist at that point, I'm not going to do that. I'm going to do Alzheimer's instead. And he looked up from his desk with this look like, oh my God, I've hired a crazy man. And he said, well, if you can make it work, I'll back it. And I did make it work, and he did back it. And I'm forever grateful about that. Now, I'm going to go back a little bit because I want to emphasize the scene here, which is an optic flow field, the visual motion that you see as a result of your own movement through the environment. It's not something you're very aware of. In fact, very often you have to tell people about it. But when you point it out, they recognize it. That optic flow field was first described by a guy, a psychologist who got drafted during World War II, and Gibson. And Gibson, well, you draft a psychologist in the middle of a war. You know, what do you do with him? Well, for God's sakes, don't give him a gun. Somebody's going to hurt someone. So they asked him, figure out what makes a good fighter pilot. And he spent the entire war and the rest of his career working on things like the optic flow field, that pattern of visual motion that we see, that kind of Star Wars pattern that gives you that phenomena of vection, the illusory sense of self-movement, and also tells you about the direction of your self-movement and where you're going. So I had studied that kind of phenomenology in the monkey, and I decided, well, you know, maybe I could use that same kind of methodology to look at people. And so here you can see I studied young over on the left, older normals, and Alzheimer's disease patients, mixing in the optic flow field with a bunch of random noise and saying, okay, how much signal do you need to consistently get it right? And that's what's plotted on the left-hand vertical axis. That's a high score would mean you need 100% of the signal to get it right. And a low score would mean that, no, you can get by with just a little bit of it and still get it right. And so that was interesting to see that young normal people just very, very consistently needed less than half of the information. And just, you know, 50, 60, 70, 80% noise, and they can still get it very consistently without any problem. One of the interesting things I discovered about this was that when you put a young person in there for this task and you say, well, okay, the dot's going to be going like this, and it's going to be, you go in there and they look at it and they look at you and go, yeah, go away. And, you know, then they bang, get right through the experiment and say, give me my $20. And so that was interesting. Whereas the Alzheimer's patients, you'd see that they, depending on how you presented the stimuli, and I'm not going to go into those details. It's an interesting detail, but it's a longer story. They would say, they'd see it and they go, well, no, I'm not going anywhere. I see that the dots are moving, but I'm not moving. And you'd explain it again, and they still wouldn't get it. They did not have the ability to extract the stimulus and interpret its meaning. And it was very consistent. They just wouldn't know. We call that visual autokinetic and boom, okay, there's another paper. But the real point was they didn't get it. They didn't get it perceptually, yielding these very high thresholds. And they didn't get it conceptually. They'd sort of lost the idea of it. And the more interesting thing was what we saw with the older adults. Most of the older adults did actually statistically not very differently from the young people, but there was a subgroup. And we never figured out what was different about that subgroup, because neuropsychologically, ophthalmologically, and neurologically, these are old, intact, older adults, mostly the spouses of our patients. And some of them, as illustrated here in the blue shaded area, had a pattern that was just like the pattern we saw in Alzheimer's disease. And I was presenting that once and found myself collecting a bunch of business cards from pharmaceutical company reps. And, you know, and I was showing it to my colleagues and they were saying, you know, because no pharmaceutical company rep had ever taken me interested in what my work before. And so I said, you know, why are you interested in this? You know, I think it's fascinating. But what? And he said, well, that's what we've been looking for. That's early detection. They're asymptomatic, they're neurologically, neuropsychologically, and ophthalmologically intact. And they have this deficit that looks just like the Alzheimer's patients. And, you know, I said, oh, yeah, I knew that. I didn't say that. I said, oh, well, good point. And that actually took my career off into a horrible, terrible direction. Yes.
Sorry to interrupt, but I wonder if it's relevant. But did you compare your tests to other tests?
Oh,
Did they, right?
Oh, yes.
They performed poorly on this one, but not,
yeah,
but they did well
yes,
on others.
There's a full standard battery of neuropsychological tests, full clinical examination, and ophthalmological examination, not done by an ophthalmologist, but done by a neurologist. So, okay. I know there are two of them, and she looked both. And yeah,
They
this
did okay
was
with that.
distinct. They were intact by those other measures, but impaired on these psychophysical measures.
So,
Please.
so did you follow some of them over a little longer term?
So actually, before I publish anybody, this is an old habit. I don't know if I'll be able to maintain it, but before I publish anybody, I always look at, okay, who's being published in this? Because now we're a couple of years, 2-3 years down the line from meeting them, and it's do I still think that diagnosis was correct? That's a very important step for me, to make sure we can go back and say, so yes, I did follow these people. And did they get worse? Yes. Did they get worse in some distinct way that I could identify as different from everybody else? No. But of course, I didn't have more psychophysics at my disposal. We were in a little lab coding the stuff ourselves. And so you could imagine doing a lot more, and I'll tell you a little bit about those ideas. So what this says is that these AD patients over on the right don't see their heading direction. Yes, they are bad drivers, and yeah, we did a bunch of work on that too. But there is some indication of some kind of continuum with the older adults, that there's some kind of transition going on here, that that's not just a random coincidence.
If I may ask,
Please.
what is the difference between out only and in and out?
Okay, so you want to know the detail. Okay, good. So, oh boy, okay, it's actually really simple. Outward is an outward radial optic flow, as if you're going forward through the environment. So you go zoom like this. You see it in Star Wars, you see it in Star Trek, blah, 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 right? It's
So there
everywhere.
is one epicenter and it goes like this, or it
Yes.
goes like this, or it goes like this.
Exactly.
So it tells you basically the heading direction.
Yeah, the heading direction is a forward direction. Of course, you could have an inward optic flow field, which would say you were going away from that heading. So it could be forward or backwards. And for some other reasons that, okay, to go into briefly, you can use strictly an outward radial flow field analyzed with a local motion strategy. You can say, well, okay, if the motion right in front of me is going this way, then the outward flow must be coming from here. And if it's going this way, well, the outward flow must be coming from over here. So you can use a local motion strategy. And if you interleave randomly inward and outward flow, that confounds the local motion strategy. You have to use the global motion strategy if you do that. And so that's why we did both. The out is an easier task, if you want to look at it that way, and in and out demands real global motion analysis.
So in and out is more or less of a noise into the visual.
No, same amount of noise. It's just a different contingency set. If either for the outward, it's left or out. It's left or right from out, right? But in and out, it could be left or right or out. You see, if you have the outward radial flow, the motion here is going to tell you that it's coming from over there. And the motion there will tell you it's coming from over there. So all you have to do is right here, use a local motion strategy. But if you have a randomly interleave in and out, you have to use the global motion optic flow analysis. And we discovered that in people, and this is the fun thing. You know, most of these ideas came from the work in awake monkey neurophysiology. And so we had a monkey who was doing it the wrong way in a complex experiment. And I had just, been thinking about this human experiment. And I said, gee, maybe the monkey's doing the same thing. And so we threw in and out at the monkey, and he made 100% errors in the wrong direction. So we went, oh my God, that is what he's doing it. So we shifted it, and then we saw it in the single neurons. The single neurons in posterior parietal cortex area, MST, completely shifted the way they did, the way they processed the information. That's an aside. I wasn't going to go there, but he asked.
If I don't get it this time, then I will ask you again offline. But what that in and out is basically two different mixed directions.
No.
No?
It could sometimes be in and sometimes be out, but it's unpredictable. It's a random assortment of in or out. You don't know that. So the efficient strategy that people, parenthetically monkeys, do is just use the global motion. But the Alzheimer's patients can't do that.
But they're steady at that time, right? They're not moving. Are they moving?
Oh, physically? Oh, no, no, they're sitting
They're
in a big
sitting,
chair.
it's just
in a-
pure optic flow.
Yes, pure optic flow. That's right, exactly. Yep, that's the whole thing.
I will
Good,
look
good.
at the paradigm myself.
Oh, good, good, good. No, thank you. So, being a neurophysiologist, I said, okay, I want to do neurophysiology with that. And so, I set up a way of recording. You can see very rudimentary thing. I mean, we didn't make the amplifiers ourselves, but it was more or less like that. We wired stuff together and started recording optic flow field evoked potentials, what we call offers. And we started recording people from those same groups, the young and the old and the AD, just to see what kind of optic flow responses we'd get. Now, I had at that time just come back from a meeting in Germany where I was said a little bit about I was going to do this, and I was told, oh, no, don't do that. That'll be a waste of time because you're going to have all sorts of different directions mixed together on the screen, and you're not going to get any kind of response out of it at all. And so and this was generous, good advice from leaders in the field. And I took it very seriously, but on the flight back, I said to myself, wait a second, I've spent the last decade or so or more or longer showing that there are specific neurons that analyze these patterns. So I'm going to find out if they're right or not. And so I went ahead with the experiment. And to make a long story longer, we did get distinct optic flow field evoked potentials. And those good guys back in Germany, when it was published, were very good about it. Saying, yeah, okay, you're wrong. The blue lines here are our older adults. The red lines are Alzheimer's patients. And what you can see from these posterior, this unique recording montage that we created, that the older adults have much bigger optic flow, N200 responses, negative responses, 200 milliseconds after stimulus onset. And the Alzheimer's patients have rather small ones. Now, just to go a little bit further, because you've been tolerant of it, if you look at at Alzheimer's patients who specifically are impaired and can't see the optic flow, the ones who are significantly impaired, the top of that previous figure, their red lines, their optic flow are flat. They get nothing. So that has been intriguing to me. Now, the real important part of it for me was when we put those perceptual thresholds that I saw you before, those N200 amplitudes, and then about 10 other things into a multiple linear regression to see how can we predict real on-the-road driving scores, that navigational score. Sorry, that's actually, I apologize, that's a different experiment. We did that too, but this was navigation in our hospital lobby. The hospital had just built a brand new lobby, so I knew no one knew that space. So I could bring all my patients in and push them around in a wheelchair and work with a couple of neuropsychological colleagues to create a test system for that, a testing battery. And we came up with scores that made good sense, blah, blah, blah. We went through that whole validation process and said, okay, this is a good measure of ability to navigate in a new environment. The other good thing about that, pushing people around in wheelchairs, was you don't have to negotiate with anyone for space. You just do it, and they'll read about it a couple of years from now. And so we did that. And of course, that MLR, the regression analysis, yielded an R square of 0.95. Meaning if we put these basic visual metrics together, we can predict who is going to be successful and who's going to get lost in a natural architectural space that people navigate through all the time. So these visual motion impairments cause getting lost in aging and AD. The blue dots, as before with the lines, are the older adults, and even they by themselves make a significant correlation. And if you put them together with the ADers, you get that 0.95. And very importantly, with all of the, with all the variables that we put into that MLR, memory didn't make any difference at all. It wasn't a memory deficit. They weren't forgetting that it wasn't anything like that. It didn't have to do with memory. And same thing driving on the road, just doesn't correlate with memory. It correlates with this unique deficit in interpreting the visual pattern that surrounds you during self-movement. With how you might be moving in the environment and the structure of that environment. So wanted to take that a little bit further, a lot maybe, and say, okay, how does that relate to cognitive processing? Where is this going on? Okay, MST, the back half posterior frontal cortex is my favorite place in the world. But that's a good reason to have that bell go off your head. Yeah, that's the thing I want it to be. Is it really? And so we created a attentional shift paradigm that's commonly called the Posner paradigm, because Michael Posner devoted wonderful works to that for years and years and years. And it's basically, I'm going to tell you, okay, which hand moves? Is it going to be my right hand or my left hand, or whichever way you want to look at it, left and right. And I'm going to flash on a cue, and then there's going to be a flow field from either that side or that side. And I want you to push a button saying, where's the flow field coming from? So if we give you a cue over here, and then it comes over there, well, that's a valid cue. We cued you to the correct location, and you're going to be much faster with that. Whereas if we cue it over here, and then the flow is over here, there's going to be a delay. And that's called a validity effect. If it's a valid cue, you're going to be faster. If it's an invalid cue, you're going to be slower. And so we looked at that validity effect that Michael Posner. Now, Michael Posner did describe that in the late 60s. I remember as a graduate student, I wasn't a graduate student then, but I was a graduate student when I got the book. Of course, Helmholtz had done it in 1896, but no one knew about that. So it's still true. And so this is a way of looking at the brain waves, and I think a little bit, well, a lot fancier, but also more useful way, other than looking at the brain wave. This is an orthogonalization of the EEG signal by power and synchrony. And this is a power plot where red means there's a lot of power, that's frequency. And what you can see is there's an N200 wave, which represents the posterior parietal cortical, MST, firing off. And then there's this other peak that we described. And then there's the P300, which is basically that signal arriving in the front half of the brain. And so we looked at that. And in the synchrony as well, and the synchrony signal actually seems to show it more distinctly. You get this big N200, which is the posterior cortical response, and then you get the big P300, which is the response of that signal once you send it forward. And then you see this weird thing in between, which we call the N2VI, meaning it's valid, invalid. And you can see in the valid cases, it's small, and in the invalid cases, it's big. And so there's a real signal there about what message the back half of the brain is sending forward to the front half of the brain. No, it's not over there, it's over there. And so that signal we thought was an interesting thing to look at and to focus on, a cognitive ERP, because there's no physical event that's corresponding to that. That's just an internal process that is synchronized with the signal, because that's the information on which that response is based. And so we then looked at older adults, the second row there. The first row is just a replication of the previous slide figure. And here we see the same thing, power and synchrony in young people and old people. And the first thing you see really surprised the heck out of me was that, yes, that N200 basic cortical response to that stimulus is way more powerful. It's a way bigger response. And you can also see that that N2VI, that messaging signal, is approximately gone. It's just not there. That's the young, that's the old. Young, that's the old. And so, okay, that makes it harder for them for sure. And then when you look at the Alzheimer's patients, well, yes, the N2VI is still gone, but the P300, that whole response in the front half of the brain is gone. I mean, there's a little bit of response you see in power. In synchrony, it's just noise. Yeah, there's some power in that noise, but you're just sending a noisy signal forward. And the P300 synchrony goes off. The power still maintains because it's still firing, but it's what is called incoherent. And people argue about the use of that word, but it's pretty accurate with regards to it. So what we've seen is this enormous change with aging, where the N200, the basic visual posterior association cortical response, gets way bigger and way more synchronous, comparing that with that, that. And then in early Alzheimer's disease, it collapses. It's gone. They don't get an N200. They don't get an N2VI. Please.
So the power reduction and more introduction of noise in between the signal, is that a correlate of a cortical atrophy? Because, you know, they have cortical atrophy, they have less cells to generate less signal, more noise, right?
So, it could be, and I can't say that is or isn't. Is it atrophy or death? But the cells aren't talking
Or
anymore.
misconnection.
Or yes, absolutely. Although, you wouldn't think that there would be a primary visual or an extrastriate visual cortical disconnection at that point, but it's an interesting idea. And it gets to something I wasn't going to talk about, and I promise not to go too long, but just to make the point that yes, there's that loss of power in Alzheimer's disease, loss of power. There you can see the synchrony is preserved, but this response itself is much, much smaller. And so Alzheimer's greatly reduces that N200 power and its synchrony. And so together what we see is that these cognitive ERPs show hyperexcitability and incoherence in aging. And in AD, they show unresponsiveness and the perceptual cognitive impairments that I showed you before. And please.
Sorry.
Yes.
So it's the coherence between the frontal and the parietal, is that in
So,
general?
Right,
more or less?
yes, yeah, so,
Okay.
it's.
So how do you know where the problem is? Right, so
Yes,
is that a
right.
frontal, so when you're saying frontal lobe and you're saying Alzheimer's, I'm actually thinking vascular, right?
Okay.
So vascular dementia, I mean, you have, that's the frontal lobe affected
Yeah,
in a
great.
big way.
So, okay, but I hope you don't mind a bit of a digression for that, because in fact, that is the big question in my mind. What's going wrong in this system? Because whatever's going wrong early on in this system, it seems to lead to Alzheimer's disease. And that's an important question right now about, well, what is it that happens in the brain that leads to Alzheimer's disease? And the critical fact that I'm relying on as the pretext for all of this work is that aging is the #1 risk factor for Alzheimer's disease. And so it demands that you ask the question, is this aging hyperexcitability possibly triggering some neuroexcitotoxicity and promoting the development of Alzheimer's disease? Is that what's going on here? And all of that other stuff, we think about, talk about, and work with our patients about every day, that's secondary to what the real pathophysiology is. The real pathophysiology may be that excitotoxicity. Please.
So this signature that you're showing us,
Yes.
not older adult, and in your previous slide, I think it was slide 2, you showed us there are 2 populations of older adults. One of them have kind of like more like an Alzheimer disease kind of response, and the
Yes.
other one have different
Yes.
in terms of that. So this signature that you show us, is it for all of them or for some of these?
Well, it is all of them. The sample size isn't that big, it's about 20 people, so for a group, something like that. So
how
they're
would you say
all
if this-
together there. And one of the things, the rules we play by is you don't just, because you got an idea, divide up your sample population this way because I like them and these I don't like them. And so I'm going to show you that separately. No, we don't do that. And so it was all comers. It's everybody in the study.
But did that actually kind of influence you?
Oh,
Like,
it
fix it?
begs another question that if you don't mind, I will get back to. Let me just go through and get back to that point because, okay, so what if you do start cherry picking? What do you get then? But I want to get to the point that what we're looking at seems to be potentially a version of excitotoxicity. Glutamate is the current fashionable favorite mechanism, glutamate excitotoxicity. There are many varieties of it, and there are many varieties of balancing systems to block excitotoxicity. And this is just from what I thought was a fun review article. But the bottom line is that glutamate excitotoxicity could be a final common pathway that leads to Alzheimer's. Very diverse mechanisms, but of course, we're talking about a very diverse patient population. If you started out in the Alzheimer's the way I started out a long time ago, or if you did now, you'd think, okay, Alzheimer's, and that's what everybody, oh, they're all alike, they're all the same, apple, apple, they can't do that. Just ain't so. I've been, my experience has consistently been for week after week, you can go forever. And I remember saying to my tech in Rochester, who I worked with for 25 years, whatever happened to what we started to call vanilla Alzheimer's? They have memory, they get all this other stuff all the time. And yes, you prove to yourself that it is Alzheimer's. You scan them, you tap them, you do kinds of things like that convince you, and you follow them over time, and that's what really convinces you. That diversity may match the many different ways that you could get to excitotoxicity, so that excitotoxicity could be that final common pathway. So what's next? So the things that's next for me is to look at whether or not this is generalizable. Are there other visual subdomains that show the same effect as optic flow, or is it just optic flow unique? And I love to say optic flow is unique because I'm Mr. Optic Flow and I've been that for 30 years, but yeah, I can't buy that. I can't convince myself. So do other visual subdomains show the same effect? And across those other visual subdomains, do they all show the effect at once? Or do you get this one over here first, and that one second, and that one third, and that one fourth? Or do some people get that order, another one gets this one first, and that one first, and second, and that one? How does this work? And then, of course, the point of all of that would be causality. I mean, could you show that the version that develops this hyperexcitability first is the one that goes on to non-excitability first, and is the ones that show the focal atrophy that you would see in imaging or in tissue if you had that opportunity, and that you could say, okay, there is a causal link. Not to say it's a direct causal link. I don't look at the excitability as a fire in the brain. I look at the hyperexcitability as an indication that something's going wrong that we didn't know about before. And that, boy, if you've paid any attention to the Alzheimer's literature, you've got to be able to sit back, if you're a non-combatant to this thing, and say, these guys, but you're either going to say these guys don't know what they're talking about, or you're going to say they're missing something. And that's the response that I get, because I have enormous respect for my colleagues. The vast majority of what you hear is we are all in the same fight, trying to do better. We're devoting our lives to it. We don't want it to be useless. We want to come up with something useful. And that doesn't mean, well, let's just keep trying 10,000 things. No, it means understand it and then try things that might work. And that's been what my hope all along. And so for the new experiments, what we'll do is we'll test the optic flow stimuli as we did before, but also do motion defined objects. You know, you have a random dot of motion, and then over here, there's dots going like this, and that pops out. You see that little circle, is it here? Yeah, no, here's a little square. But you can have a circle or a square or pop out on the left or pop out on the right. It's a very distinct perception, and it's mediated by more posterior cortical areas than words. Words are processed the same kind of way. You can give a word like C and put a funny letter at the end, and okay, on the left or on the right, and you can ask them push what letter does the doesn't belong there, one on the left, one on the right. And you can do the same thing like this with non-language shapes. And fortunately, I forget the name of them right now, there's this great universe of non-random shapes, very systematically derived. And so we stole that and made those patterns out of it. And of course, faces, all due respect to our First Lady, but that face could either be looking to the right or looking to the left, or you see it to the right and the left. And you push that button. Okay, which way are they looking? And just the same way you could do that. What famous scenes here? The Pathophysiology. Are you looking at it so that it's facing the left, or are you looking at it so that it's facing the right? Which is it? And it turns out that, surprisingly enough, we came up with this set. We came up with a much bigger set, and we narrowed it down to this half dozen, where just about everybody can do this task at 100% coherence. That's what we were looking for, something that we knew that, okay, everybody could do. And it's not a big, long explanation, but we didn't test abnormal people because just as we were getting this going, we were all ready to go, and the IRB application was approved, and then came COVID. And, so COVID, I think we can all agree, has been incredibly inconvenient for all of us. And that not to overlook the horrible tragedy that COVID has been for so much of us. It's so many of us. And not to also overlook the fact that this back half of the brain processing system, of course, is controlled by those frontal attentional top-down projections, frontal parietal and frontal occipital projections, and they feed forward into the hippocampus, which is where memory is. And most people think, oh yeah, Alzheimer's disease. I mean, I've had senior neurologists, Alzheimer's disease. Yes, that's a memory disorder. If you don't look well, if you spend your life working on something, you develop a very distorted perspective of its importance, right? So what are we going to do? We're going to use several different paradigms with those 6 stimulus sets. A perceptual paradigm, straightforward psychophysics, and straightforward ERPs, but across those 6 domains. In aging and Alzheimer's, we always throw the young people in. They're easy to get. They allow you to test out the system and make sure it's working the way you want. For $20, they'll do that, and they'll come and work. They don't take, they're young, smart, college students, people from our classes and stuff like that. We don't twist anybody's arm. We just dangle $20 on Friday afternoon to a bunch of college kids who don't have any money. You go, okay, I'll do it. It's not going to hurt, is it? No, I don't think so. And then we'll do this attentional paradigm you saw before. But instead of doing it with just the optic flow, we'll do it with all those other stimulus sets. And then finally, we'll do something that takes me back to my freshman year in college. Because in college, I had this, I needed a job. And so I got a job cleaning rabbit cages. And when I was cleaning the rabbit cages, I could see there was a new faculty member who had just come from Oslo, working with Per Anderson, who sort of invented the hippocampal slice. And he was trying to set up a slice lab. And this is a guy who, well, he wasn't all that comfortable with tools. And I had grown up in a firehouse. My dad had been a fireman, but was the mechanic for the fire department when I was a kid. So I really did grow up in a firehouse. You could never do it now, but eventually laws against stuff like that. But I had a great time. We went to a lot of fires, saw a lot of interesting things, stories some other time. He eventually said to me, would you like to work on this experiment? or would you rather just go on cleaning the rabbit cages? So I thought to myself, oh, is this one of those trick questions they taught me about in college? And so I said, no, I'd rather do this. And I spent my entire college career doing hippocampal slices and looking at long-term potentiation and habituations and all this stuff too in development. And then at the same time, I did the anatomy over with Pashko Rakish, who was at the Children's Hospital. And then I repeated that in the monkey stuff, doing the anatomy of and that's really interesting stuff. Golgi stained anatomy is fascinating. And so, well, that'll let us look at memory mechanisms, memory for optic flow directions, memory for shapes, memory for words, memory for spaces, places, spaces, whatever you want. And look at that, because what's the hippocampus? The hippocampus is, many of you may be hippocampologists and know more about this than I do, but it's essentially a stack of coins, like a pennies. And each coin is connected to a different part of cerebral neocortex. And it's getting that information there, and then it's putting it all together. You don't know what putting it all together means, and it ships it up to the brain, right through Pape's circuit. And then you store it up there somewhere. But somehow or another that works. Seems unlikely, doesn't it? So that's the story I wanted to tell you about. That's where I am and how I got there. I can't imagine there are any questions, but if you do have any questions, I'd be happy to hear. Please.
So very nice, first of all, really fascinating.
Thank you.
Initially you showed us the change, like the prediction of Alzheimer's in these older individuals.
Yes.
So a lot of faculty in my department do biomarker identification.
Yes.
Being criticized by, I don't want to know about it if you can't do anything about it. So you do something about it.
Right.
You get insight into the mechanism.
Absolutely. So, and in fact, I think that's been a very dominant sentiment in the last 20 years. I mean, this is the era of Francis Collins running NIH and saying, okay, our point is to come up with new pills for pharmaceutical companies to manufacture and help people. And then, of course, there is the, let's just say approximately 200-year history of modern medicine, which says, you can randomly throw all sorts of crap at all sorts of people and get all sorts of weird results. But if you don't understand what's going on, you're not going to be able to find real cures and real treatment. If you look at hypertension, if you look at infectious disease, if you look at cancer, it's always been the case of figuring out what's going on is what leads to effective treatment. And that is, I think, the basic science lesson to modern medicine. Don't throw away the baby with the bathwater because, oh no, we understand now everything. We're just going to find the right pill any day now. Yeah, I want the right pill too. I very much want the right pill. I think that there are going to be lots of right pills. Look at hypertension. How many different antihypertensives do we have? It's hard to get 5 patients in a row that they're taking any one, except Lasix. A lot of them take that, which is a good strategy. Nothing against it. But the idea is that that's for the heart. Do you think the brain's going to turn out to be simpler than the heart? Now, I don't want to offend anybody, but come on, it's just a pump, and so I think that the idea of figuring out how it works and how it goes wrong is fundamental to developing effective treatments. And Alzheimer's disease, although it's very important for growing populations, growing older populations all over the world, make no mistake, every projection is that Alzheimer's disease is going to devastate every healthcare system in the world if we don't do something about it. It's that urgent because the population is getting older that fast. We have to actually do something about it. And my strategy is, okay, we could keep guessing, or we could try to figure out what the hell's what's going on. So that is my perspective. And that's what I would say to him and to Francis Collins. I just do MD PhD. He went out back to California. When he went out interviewing, he went to a talk that Francis Collins gave and said, if you're not working on developing a small molecule for the pharmaceutical industry, you're wasting your time. And he came back and told me that. I told you not to go to Washington. Talking about wasting time. I love Washington. DC is a great place. But when he was out interviewing, he had the interviewer who said, well, I understand you're interested in the brain and all that, but you've got to work on something smaller. And he said, I work on electrons. Do you work on something smaller than that? And but it's, so repartee back and forth, which is fun and part of, you're going to hang out with smart people, you got to expect it. But the truth is, we're following the first principle. The first principle is understanding leads to efficacy. And that's, I think, the real lesson of modern medicine, because we have been incredibly successful and we need to solve this problem. But Alzheimer's is just the tip of the iceberg, because behind this analysis of the function and dysfunction of the human brain is all of neuropsychiatric disease. And we need to start getting real about it, because if we haven't noticed, we're killing each other off at an incredible rate. And we have to start understanding what's going wrong. And so let's roll up our sleeves and take seriously our obligation to fix the greatest plague that's facing mankind. And that is bad behavior, whether it's in old people or young people or people in between. And let's try to do something about it. That's the challenge for medicine in the 21st century. Now you've got both the lecture and the rant all for the same price. and I appreciate your patience. Thank you.
These experiments, Dr. Duffy, this is with EEG.
Yes, you're just putting electrodes on the heart. It's just like an EKG. What?
ERP, you call it event.
Yeah, so what you're doing is just syncing off of the onset time, which down to about the millisecond, a couple of milliseconds. And you're averaging based on that. And this is what the brain does. Every time you do that, it makes that sound. And you can, if you set up an experiment that captures how the brain really works, like the attentional paradigm, you can see. I didn't show you these figures, but they're nice, pretty pictures of heads with color, blah, 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 blah. You can see, okay, this signal is coming from there, and this signal is coming from there, and this signal starts here and just sort of pushes forward, and then there's one that comes back. You can see that. I think that's just way cool, and I'm interested in it. And you can also do it in imaging if you can do it for $10,000 this way, but if you've got $10 million burning a hole in your pocket, we can do that in MRI. It's a little bit more problematic, but if you have an upright MRI where people can sit in it, that works a little bit better. It's less disorienting. But you can do a lot of stuff in a lot of different ways. I'm always trying to find the simplest, fastest, easiest, cheapest way.
Yeah, but with EEG is also time resolution is great, right?
Exactly.
So you can follow the signal.
Exactly. That's the critical difference. And it's also confounded by the neurovascular. The MRI is only the neurovascular response, which changes enormously and aerially with aging.
Oh, that, yeah.
So, right. So let's just listen to the neurons, has been my approach.
Right.
It's not a prejudice. I'm a neurophysiologist. I know how to do this.
Yeah, so that EEG training helped you, huh?
Yes, actually it did. It did. I still love it. I love patient care. I don't, it's, oh my God, look at my schedule for tomorrow. Yeah. We all go through that. It pains us. But once you get in there with patients, all that goes away. And it's like, what the hell's going on with this one? I had an Alzheimer's patient on Friday. And I was, writing it up afterwards. I'm saying to myself, I've heard of something like, well, yeah, this is Gerspun syndrome. Yes, and, it just, You know, oh yeah. It was useful to take the boards a long time ago. Well, thank you all very much. It's been a real pleasure.
Thank you.
And have a good day.
How many subjects in each group will you need? So what's your,
Fewer than I see in a period of 3 months. I mean, I see a lot of patients. And yeah, I mean, now, like I say, I don't go for
that's a
all of
lot
them.
that's a
I
lot
want
of-
vanilla AD without the chips and the nuts and all the other things
Yeah,
that
I
get mixed
see.
in.
So, no, but I mean, it's a group of 20s now?
Oh, so,
I mean,
so,
but
yeah,
I'm just
so,
asking for power.
oh, absolutely. So 20 was,
Does the
you know,
signal
other,
is strong?
right, you don't want to get into this data I showed you. You don't want to get into this chasing your tail of trawling for p-values. You want it to be significant. So the real story here is I did another experiment before this with that guy who told the other guy, yeah, I work on electrons, you know, wonderful, wonderful guy, a brilliant guy. And we did a different experiment with a paradigm that I had proposed in my dissertation defense. And we finally got to do it. I wanted to do it at some point. So we did this experiment, flashing different stimuli at the same time at different frequencies, and then using frequency decomposition to find the signals for each one. It was a really interesting way of manipulating attention. Did all that and got results like the ones I showed you, but you can't look at them that way because the frequency thing. I could show you those figures with that. And you know, it got published nicely, but we got this criticism of, well, that's a really weird experiment that no one's ever done before, and we don't know how to interpret this result with the hyperexcitability and the collapses in AD. And that's when I said, okay, I'm going back to ground truth cognitive neuroscience, a Posner paradigm. You know, Helmholtz to Posner, it's been the same for over 100 years. Let's use that. And those are the results I showed you, just vanilla cognitive neuroscience. And the effect size is actually bigger in this experiment. So I'm glad they made that suggestion. No one suggested the Posner paradigm, but they said it's got to do something, you know. So then you're reading that review and go, okay, you know, I need to use something that everyone will accept. And Michael Posner's thing would do it. So that's where that came from. Again, thank you all very much. For a pleasure to meet you, and I hope to have the opportunity to work with you.
Yes, yeah.
I don't know how to shut this off.
Thank you.
Oh, my pleasure. Thank you for having me. We appreciate it.
About various opportunities.
Oh, well, hey, you know, I'm very excited about the opportunities. I'm very excited about the collaborative opportunities. I'm excited about working with people who are going to tell me what those excitotoxins are. I'm excited about working with people who can come up with